Okay, so in today's class we'll continue with phase noise again. Okay. So before that, if you look at the LTI analysis, I think Siddharth was asking last class what happens if you consider the negative resistance of the tank. I don't know, did you have a chance to work it out by yourself? You did. It works out, right? I thought I'll just do that in class anyways. Okay. So let's say the negative resistance of the tank is some minus RA, okay, and the parallel resistance is RP of the tank. So you have some noise which is being injected into this, okay. So what happens is, right at the frequency of oscillation, you know the condition is your RP has to be equal to RA. That is the only way you'll have oscillations. However, if you move away a little bit from the center frequency, that won't be true anymore. Obviously, it were true. If it were true, you'd have an ideal LC tank, right? You won't have any problems. You won't have any noise. You won't have anything. Okay. So definitely that's not true. Okay. So in general, your R equivalent will be minus RA RP over RP minus RA. Okay. How about the value of this guy? Once you move a little bit further away, it will be a little bit greater than RP, slightly greater, not much greater, and that also depends on how far away you move, obviously. Okay. So this will be the value of the equivalent resistance, and it will be almost equal. So which means this will obviously be much greater than RP.
Minus RA will not, it should be greater than RP.
Yes.
By design.
Okay. At resonance, minus RA is going to be equal to RP, right? At any other point which is not at resonance, all the losses will not be compensated by the active circuit.
So you cannot say it is RA and RP, right? The effective impedance is what will be.
You should actually, so we covered this in class, one of the first VCO classes, which is when you have two resistors in parallel, if you want the negative resistance to be more prominent, it actually has to be less than the positive resistance. You can actually work it out yourself. You can check out the notes, right?
But I understand.
Yeah.
What I'm trying to say is that you cannot say that RP is less. You have to say that effective impedance of that RLC combination is less.
No, the effective impedance of the RLC combination is going to be positive. That you can say.
Okay.
For that to be positive, RA will have to be greater than RP, right? Isn't that right? Okay. So your R equivalent is going to be RA RP over RA minus RP, which is obviously much greater than RP, right? Because RA minus RP is very small. So you can define an equivalent Q, which is omega naught C times R equivalent, which is much larger than Q, the original Q. Okay. And again you can go through the same calculations which we did, except now you have G equivalent, which is 1 over R equivalent. So you can find out the admittance, right? G equivalent, the imaginary part stays the same. This one stays the same. Okay. Let me just actually let's just do it this way. So it's 1 over the admittance. Okay. This will end up being, You can just follow the same procedure what we did. Right? This is what we did, except instead of R equivalent, we just had R. Okay. Now you know your Q equivalent is much larger than is very large. Okay. So if you are sufficiently close in offsets, your Qs can be probably in several hundreds or thousands. Your Q equivalent Q. Okay. Because a portion of the losses in the tank have actually been compensated for by the active circuit. Okay, so now this approximation that the second term is much larger than 1 is definitely valid. Okay, so now you can neglect this guy. Well, we should make it 0, just neglect it. Okay. So, what is R equivalent by Q equivalent? Is it's the same as R over Q, right? Because your Q, oops, sorry. Okay, so obviously your R equivalent or Q equivalent will be R over Q. Okay, so you end up getting the same term, and after this it's pretty straightforward. You just proceed with the same thing. Okay.
That is RP.
Sorry, yes, it's RP. That should be RP. Okay.
Q is equivalent Q is large irrespective of the frequency.
Equivalent Q will, okay, so if you consider at the frequency of oscillation, obviously there is no the effective resistance as if, effective Q looks as if it's actually infinite because you don't have any parallel resistance at the frequency of oscillation. If you move just a little bit away, your Qs will be very high. Okay, so it will probably be in, yeah, you can calculate it out for a particular offset.
Closer to
The higher the Q, definitely. Okay.
Maybe I missed the usage of you are making RA greater, modulus of RA greater than RP. So L and C cannot cancel out each other completely. So
Why not?
If they cancel out completely, then you will have a negative resistance part and the amplitude will become amplitude is limited by the non-linear.
No. If RP is, are you talking about RA greater than RP? If RA is greater than RP, then the amplitude will actually fall. It won't increase. If you have minus RA and parallel with RP, and RA is mod of minus RA is greater than RP, your amplitude, the effective, you will get a positive resistance. You won't get a negative resistance. You can calculate it out. Okay. So the actual condition we want is actually that the negative resistance should actually be smaller than the parallel resistance of the tank. Okay. So now let's move on to the Hajim model. So we looked at this briefly last class. So the basic idea is actually you don't even, so let's say, so what you do is you inject some noise into the tank. So let's say even take an LC tank, right? You're going to inject noise at different points and find out when the system is sensitive to noise, to create phase noise. Okay, and your T is your observation time. So you're starting observing the signal at a particular point, but your tau is your excitation time scale. Okay, so you have two variables here. One is t, other is tau. So if you actually look at some noise which is injected here, what happens? You will see some amplitude change, and then but the zero crossings will stay the same. Okay, so any noise which is injected at the peak will not convert into phase noise. So in other words, your so this is your delta of t minus tau. So that's where you are injecting your noise. Okay, and similarly inject something here, we'll get this, and the phase of the oscillator will change. So we know this. Okay, now so you're going to remember we talked about it being, yes. So okay, so what will happen is for the immediate cycle the amplitude will change. Okay, eventually what will happen is because you have an amplitude limiting cycle, eventually it will come back to the right amplitude. Okay, in a few cycles depending on how strong that is. Okay, so definitely if you have some AM noise, you know that that's going to be removed by your limiter. Okay, the point to note is that it never registers, the zero crossing doesn't change. Okay, so it won't change into phase noise. Okay, what you can do is you can take a look at, okay, how do you explain this better than the figure? Let's see. Which whole thing? Okay. Yeah, I mean, what you're talking about is like a DC extra charge into this. Yes, that could also happen, definitely. So, you're actually, let me see, could it have a DC component? If you have a DC component, what will happen? Actually, I'm not sure. Let me think about it. Okay? Let me think about it.
Sir, why are you considering only at the zero crossing? Even if the pulse is slightly like near zero crossing, it will change the.
Yeah, so these are just the two extremes. These are just the two extremes. What you're going to do is, finally when you build the noise model, you're going to take into account noise injected at all times, because in reality noise is being injected into the tank at all times, definitely. Well, the thing is, the impedance of the tank at DC will be zero, okay, because of the inductor. That is definitely true. So you can, even if it won't create a voltage, even if you inject a DC current, that is true. It will all be bypassed through the tank, right? That is perfectly valid.
Actually, the peak of the cycle capacitor is fully charged, and when you inject current, you will go with the capacitor and you will
Yes, that's right.
But in the zero crossing point, I think inductor current is not, like current actually energy is stored in inductor.
Yes.
But there is a shift in,
So there is a shift in what?
and that's why there is no DC shift.
That's why there's no DC shift here, is what you're saying. Because there is because the current is flowing through the it just adds as charge to the capacitor, is what you're saying. Because the you're saying the current through the inductor cannot change suddenly. Yeah, that is definitely another way to look at it. Yeah, definitely that's another way to look at it. Okay. How can it happen? So what will happen is this, okay, you're right. So what will happen is this side will be slightly smaller, but what you have to see is for the first, okay, I don't know how to, well, let me think about, if I see if I can explain it better. Okay, next class maybe I'll think about it a little bit more, see if I can explain it better. Okay, So since your signal is very small, your noise which is being injected into the system is very small. You can think of a impulse response. So it's still a linear system, but a time variant system. Okay, so you'll have an impulse response which is dependent on tau, which is the point at which your noise is injected. Okay. So you can define the impulse response. So what you're going to do is you're going to define it in terms of a couple of parameters. Okay. So at t minus tau you're applying the impulse, right? So what you're going to do, so you define something called the impulse sensitivity function, which is normalized by dividing with q max. Okay. So what you want to do is find something which you can compare across different circuits. So that's why you're trying to normalize it. Okay. So your gamma is going to be dimensionless. Okay, and it's going to be periodic with period 2 pi, because it depends, it follows the signal. So now you can write your phi of t, which is your total phase, which is just the impulse response times your excitation, which is your current noise. Okay. So what you are doing is your noise current is being injected into the tank at all times. Okay. So what you are trying to do is to find the instantaneous phase at t. You are trying to calculate all the phase perturbations which has happened till time t. Okay. And for each instance when the noise is injected, there is going to be a certain gamma. Okay. So you are just multiplying the gamma by the I of t and then integrating it from minus infinity to t. Okay. Yeah. Okay. So since gamma is periodic, you can also split it into the Fourier series, decompose into the Fourier series components. Okay. So you have the DC component and components at all frequencies. Okay. So we saw the so let's do a couple of things. Just for example, we'll look at the gamma for an LC oscillator and a ring oscillator. Okay, we'll see what it looks like. So the way you find, okay, so the best way to find gamma is actually by simulation. Okay, so you take an LC tank or an LC oscillator and keep injecting small pulses. Okay, make sure you inject small enough pulses such that linearity still holds. Okay, and then you find out the change in the output phase. That itself will tell you what gamma is. Okay, so that is the best way, the most accurate way, best way. Okay, there are some analytical techniques. Typically for very common signals, it will usually actually be, if you have V0 of t, it will usually be dV0 by dt. Okay, usually, or something proportional to that. Okay. So this. Okay, or let's just take cos omega naught. The amplitude, the proportionality factor doesn't matter. Okay. So if you do this, gamma happens to be minus sine omega naught t. Okay, which is as expected. At the peak, it is least sensitive. At the zero crossing, it's maximum, and so on. How about the ring oscillator? So you'll get pulses right at the zero crossings. It will look like that. Again, if you differentiate the waveform, you'll get pulses at the zero crossings or the rise and fall instants. So now we put in gamma into the Fourier series expression into the phi of t expression. That's your first term plus okay. So this will be the expression for phi of t. Okay. Now let's, before we go on to simplify this, so let's see what will happen. So you take a VCO. So your output is this, right? For the VCO. Now let's assume you have some okay. Oh God. So this will give you, if you actually look at the output, right, you can show, so this is actually a very nonlinear process first of all, okay. So you can show that, you can look at Razavi section 3.2.2, that gives you an accurate expression for what the values are, but if you do this, you will get the sinusoid V naught cos omega naught t, but you will also get two equal side bands, okay. Okay, at a spacing omega m, and this is valid for omega m, which is much smaller than omega naught, okay. Okay, so now let's also see what will happen if there is some noise at an offset delta omega from a harmonic of your omega naught. Okay, not just at omega naught. Okay, so this is your I of t. So let us say this is being injected into the tank. What is phi of t? You can show that over okay, so all you have to do is take this Im cos omega naught t, put into this expression. Okay, when m that okay, maybe let's call it a different variable. Okay, so let's call it different variable k. So what will happen is, when k is not equal to m, this integral will give you a very small number, and when k is equal to m, it will give you this term. Okay, it will give you something which looks like this. Again, you will have to make some approximations. Delta omega much smaller than omega naught and so on. Okay, so ik ck sin delta omega t by 2q max delta omega. Now what you're going to do, so this gives you the, okay, first of all, what does this mean? Even though you're injecting noise at m omega naught plus delta omega, you're actually going to see that noise appearing at delta omega from omega naught itself. Okay, sorry,
The integration.
yes,
Like cos and omega naught should without last.
yes, should it
Gamma of omega naught.
what did we have? Did we have gamma of omega tau?
Tau.
Yeah, so there should be omega tau. Yeah, thanks. So what this means is, so in general your noise profile is going to look like this, okay, versus omega. So let's say here 3 omega naught are here. Okay, so this is of course delta omega. Each of these is delta omega. So what you'll see is, let's call this In of f. So if you'll just look at the particle density of phi, so you'll just get something here. Okay, and at delta omega you'll see components from all of these guys. Okay, luckily it happens that your Cm is going to die out as omega increases. Okay, so for any real system that's true. For a physical system, I mean that's a good approximation. So typically what you'll have to see is, you'll have to take into account maybe only a few harmonics, maybe 5, 10, 15 harmonics. Okay, and then through phase modulation you will see and here again. So obviously the one to go from here to here is V naught of t that's how you get from here to here, right? That's your phase modulation. Okay. So now you are going to find your power side bands. So for if you just take the case of, let's say, ik cos k omega naught t plus delta omega, you can do the same narrowband approximation and show that the power is ik squared ck squared over 4 q max squared delta omega squared. Okay. So if you have a white noise source, so let's assume you have IN over delta F, right, which is 4 kTr, something like 4 kTr. Actually the times, you'll have to sum up all the noise currents from everywhere, from all frequencies. Okay. Okay. Now let's say your so remember Parseval's theorem. Current to the, if you sum the modulus of all your Fourier series coefficients, that will be the same as the power in the signal, right? So if you do that for gamma, you can show that this is equal to 2 gamma RMS squared. Okay. Okay, 2 q max squared delta omega squared. Q max is the maximum charge displacement across the tank, which is nothing but C times V peak. Okay. So okay, so this is the general expression for the phase noise at an offset delta omega. Okay. If you take an LC oscillator, we saw this, right? It's minus sine omega naught t if your signal is cos omega naught t. So your gamma squared RMS is nothing but half. Okay. So let's take the case of what we did with the LTI and see if we get the same answer, right? First of all, this is IN squared 4 kTg. Okay. L of delta omega is 10 log IN squared, which is 4 kTg, IN squared of delta F, which is 4 kTg, gamma squared RMS is half by 2 okay. The C times the V peak is nothing but root 2 V naught. We'll come to it. We are actually coming to it. Okay, we are going to consider that next, because right now we are just considering the impulse response, the output noise due to a white noise source. So remember that we assume that IN squared delta F is white in this case. Okay, we'll come to it next. Come to see what happens, you know, when you have just flicker noise. And if you just, you know, go through the whole thing, you know, remember the Leeson's model, we express it in terms of the Q of the tank. So you can go ahead and, you know, do everything and show that it reduces to the same thing. All you have to do is multiply and divide by omega naught, okay, and then multiply and divide by r. So omega squared r squared c squared will give you q squared, right? So that's how you get this. Okay, it's pretty straightforward. So definitely it looks like, at least for the, as far as thermal noise goes, it's pretty similar to the linear system. Okay. Okay, so what happens when you have flicker noise? So you can express your flicker noise in terms of the flicker noise corner, okay, which is 1 over omega f by omega 1 over f by delta omega. You can express your flicker noise in terms of this at an offset delta omega, at any frequency delta omega, okay. Okay, you can express it in terms of the, because you are going to assume in the log plot it's linear, right? You can express it in this form. What is your L of delta omega? Is your 10 log okay. So now as far as flicker noise goes, you know it's only around DC, okay. There is no flicker noise in and around n times omega naught. So the only term you get here is C naught squared, which is the DC. C naught by 2 is the DC of your ISF. You get something like this. Okay, this is your IN squared times omega IF or delta omega is your 1 over f noise. C naught squared by C naught by 2 the whole square gives you C naught squared by 4 times 2q max squared delta omega squared. So of course now you get the 1 over delta omega cube term. So it predicts the existence of 1 over f noise. Okay. Let's see what it tells you about your 1 over f cube corner. It's 1 over f times because you just need to compare, find out the point where this becomes equivalent to your thermal noise, right? If you equate the two, it turns out to be something like this. So this is basically so it's basically omega 1 over f times gamma DC over gamma RMS the whole square. Okay. So what does this tell you? First of all, if you have a device with a certain 1 over f corner, the 1 over f cube corner is not going to be the same as the 1 over f corner. It is going to be some multiple of that. And typically, as it turns out, it's going to actually be smaller than the 1 over f corner. Okay. So what else do you know? If you make gamma DC equals to 0, you can get a perfect, right? You'll get a very, very low 1 over f cube corner. That's what it means. So it gives you some design insight also. When is gamma DC equal to 0? It will happen. So of course, when you consider an ideal sinusoid, gamma DC is already 0. But if you take a real oscillator, you will have some finite rise time and fall time for your signals. And your gamma DC will become 0 when your rise time and fall time become exactly 0. Okay. Sorry, your rise time and fall time become exactly equal. Okay.
No 1 by f.
Yes, thank you. Yeah. Okay. Okay. So let's take two of the oscillators which we have studied. They're both cross coupled, but so if you take this case, obviously the fall time is determined by the transistor. It pulls down, but pull up is through the inductor. Okay. So in general, your rise time and fall time are not going to be equal. Okay. However, if you go for this topology, okay, the complementary topology, you can size WP and WN such that you can get very symmetrical rise and fall times, and you can try to make gamma DC very, very small. Okay. So in general, your omega 1 over f cube corner for your complementary transistors, for your complementary VCO is going to be lower, okay, than your cross coupled NMOS. So this is one of the motivations for using a complementary. Of course, the other motivation is that for a given RP and bias current, it actually gives you twice the amplitude. But we'll see if that really helps or hurts you. Next class we'll try to go into some of the VCO design, what all you need for designing the VCO, some of the procedures, and you'll see that maybe that's not all, okay, there is to it. Okay, so you got the 1 over f cube, you got the 1 over f squared. How about the flat noise? Right? So what this actually predicts is something like this. Okay, and what you will see is typically if you don't have any other circuits, that is probably what will happen, because your tank is actually going to have a response which is 1 over delta omega squared forever, or at least till a point where that the small signal approximation is not valid anymore. Okay, so that is one thing which hurts you. But probably much before that, what you'll hit is, you'll end up having to use some buffers to drive your external circuits. Okay, those buffers will end up having a thermal noise floor at the output. So it will be limited by that. Okay. And of course, finally, if you're trying to measure a VCO, let's say, even with buffers, even if your buffers are not limiting it, your measurement equipment will have an input noise floor. That could end up limiting your flat noise. Okay, but you'll usually, your measurement equipment are really good. So okay, so you'll usually hit the buffer much before you hit the measurement noise floor. Okay, so let's stop here for today, and we'll continue on Monday with the VCO design again. So I thought I can finish off this class, but I just wanted to go through the LTV noise theory, and then what we'll do is we'll cover some, I guess, each component of the VCO. We have not looked at the VCO bias. We have not looked at we looked at the varactor, but we didn't look at other things. So we'll probably have enough things to do on Monday about the VCO. Okay, only after that we'll move on. Okay, and by the way, I haven't forgotten Debashish's question about the equipment.